Okay, so in this video, we are going to look at sort of reversing the role of the bank and the individual by beginning to look at it different investment situations. The maths is exactly the same, really. It's just changing which direction the money is flowing in. So what we're going to look at here is the idea of an annuity. So an annuity is essentially a compound interest investment with regular withdrawals. So it's an investment that is set up to pay a guaranteed fixed income for a fixed period of time. So one of the most common examples of this would be in their retirement. Someone might use their superannuation savings. So superannuation is money that each time you get paid, your employer sets aside some money that's deposited into your superannuation account. That's essentially a big investment that grows over the time of your working life. Ending your working life, you retire, you can then take that lump sum of money, set it up in an annuity in a way that it then pays you regular income. Now obviously, well, there is a way that it can be done, we'll talk about that later, but that wouldn't usually be set up in a way that that money would last forever and ever and ever. So obviously you do calculations under the assumption that you're going to live for X many years and you want to be able to withdraw, X amount every month. So, as I said, calculations involved with annuities are exactly the same. Oh, the other thing I was going to say about annuities is sometimes I find that in various textbooks and exams and tests and trial exams and SACs and whatever, occasionally the word annuity is sort of bandied about synonymously with investment. So I'm going to use them somewhat interchangeably. I'm not sure that that's 100% correct. I think an annuity is really about that idea that when you retire you set up this account from which you then withdraw money. So it is really about a compound interest investment that you withdraw money from regularly. But sometimes I find that it can be used excuse me, it can be used fairly interchangeably with an investment in general, which you might deposit into or withdraw from. And so we'll revisit annuities, but it should possibly be called investments later on, where we make deposits regularly to the investment rather than make withdrawals. Anyway, so as I said, an annuity or an investment essentially acts in the reverse way to a loan. So when we have a loan, the principal value, the bank pays that principal amount to the individual. In the case of an annuity or an investment, the individual pays that principal amount into the bank. Okay. And the interest in the case of a loan, the bank charges interest, as a charge for you having borrowed their money, whereas in an annuity or an investment, the bank pays interest for the privilege of having your lump sum of money in their possession. And in terms of payments, a loan, usually the individual pays off the loan. Well, yes, the individual pays off the loan, so the individual makes payments to the bank. In these situations, we're looking at a situation where we withdraw from the investment, and so the bank will be paying the money to the individual. It's also possible, obviously, to have investments where you might continue to deposit money into the investment, and we'll look at those in a couple of videos' time. But again, essentially, it's just about changing the direction of the money flow. Okay, so in the same way, so these are essentially reducing balance loans in reverse. Okay. So in the same way that we can work with a reducing balance loan using either a recurrence relation or an amortization table or finance solver, those three things are also applicable in these situations. So the recurrence relation is here, and it's exactly the same as the recurrence relation for a loan. It's just that the individual benefits as this grows, whereas in the case of a loan, the bank benefits as it grows. So it's just about where the benefit sits, but the formulas or the recurrence relation is really set up in exactly the same way. Okay, let's work through an example. Amy plans to travel overseas for 6 months. She has saved $8,000 for her travels, which she plans to invest in an annuity, so that she can earn interest on that amount, but so that she will also have a monthly income. She invests her money in an annuity that earns a rate of 6% per annum. The annuity is paid out as a monthly income of $1,356, per month over 6 months. Okay, so we want to model the value of this annuity after n months using a recurrence relation. Okay, so the first part of our recurrence relation, remember, is V0. Where do we start? And our initial investment is $8,000. So that's the principal value of the investment. Okay, then we want to work out the recurrence part of the recurrence relation. So Vn plus 1 is going to be equal to something that happens to Vn. So Vn is going to be multiplied by something, that is the compound interest, and then we're going to be withdrawing the payment. So we're going to be subtracting the payment. Okay, so minus the payment is minus 1356, so we take that out every month. But the interest also earns, the annuity also earns interest at a rate of 6% per annum. Okay, so that means that we need to first of all work out the interest rate per month, because this is a monthly arrangement. So that's 6 on 12, so that's going to be 0.5% per month. Okay, and then from that we want to work out what is our multiplying factor. So again, if your percentage work is good, you're going to be increasing by 0.5%, so you're going to be multiplying by 1.005 every month. If you need to use the formula that's provided up here, you can calculate that multiplying factor R by doing 1 plus 0.5 over 100, and you'll see if I do that with my CAS, 1 plus 0.5 over 100 is indeed 1.005. So as I said, a 0.5% increase means you're ending up with 100.5% of what you started with. As a decimal, that is 1.005. Okay, so here's our recurrence relation. Here, listed here, V0, and then the recurrence part of the relation. Part B, we want to use the recurrence relation to determine the value of the annuity after 3 months. So after this has happened 3 times. Okay, so let's use our CAS to generate the recurrence relation. So 8,000 and press enter. Then we're going to multiply by 1.005 and subtract 1356. Okay, so after 1 month, 2 months, 3 months. So after 3 months, the value of the annuity is $4,032.22. Okay, so remember she wants to use this over a 6-month period. After 3 months, she's got about half of the money left, so that seems to be working out well. The part C, is the annuity fully paid out after 6 months? If not, how much will the final payment need to be to ensure that the annuity is fully paid out after 6 months? Okay, then this is again about sort of adjusting that last payment, which we've looked at a couple of times in previous examples. So let's work out what the value of the annuity is after 6 months. So we're up to 3 months on our CAS. 4, 5, 6. Okay, so after 6 months, the value of the annuity is $4.64 to the nearest cent. Okay, so it's not fully paid out. Okay, so not fully paid out. We haven't withdrawn all the money. There's still $4.64 left in there. Not fully paid out after 6 months. Okay. So, you know, we wouldn't leave our $4.64 sitting in the account for another month to earn a 6%, or well, not even that, 0.5% of that. It's not really worth it. So we would just withdraw that with the 6th payment. Okay, so this means that the 6th and final payment, instead of just being the regular $1,356, it'll be that plus this extra $4.64 that's sitting there. Okay, so that's going to be $1,360.64. If you need to use your CAS, adding that 1356 onto your previous value, $1,360.64. Okay, so she will withdraw her investment by withdrawing 5 payments of $1,356 and then an extra payment of $1,360.64. So if we actually worked that out, if you did 5 times 1356 plus her last payment of 1360.64, you'd expect that to actually be a bit more than 8,000, because during that time it's also earning interest. Okay, so actually over the course of the 6 months, because she had it in the annuity where it was also earning compound interest, even though it was supporting her, she earned an extra $140.64 during that time. Okay, let's have a look at an amortization table example. So the annuity that we just showed in the previous example, so the holiday, what was her name again? Amy's holiday, can be also summarised in the amortisation table below. Okay, so we look at the payment number, the payment that was received, so rather than the payments made, the interest that was earned by the individual, and the principal reduction, and the balance of the annuity. So we start off with a balance of 8,000. We make a payment of we withdraw a payment of $1,356. The interest earned on that payment, so that's going to be our 0.5% of 8,000. Okay, so if we were to work that out, sorry, 8,000, 0.005 is 0.5% as a decimal, times that by 8,000, and we see indeed that's $40. Okay, so that's the interest. And then the principal reduction is going to be the payment that we've withdrawn, sorry, that we have withdrawn minus the interest earned. Okay, so that's how much we're actually reducing the principal by, because essentially $40 of the payment that we've taken out was interest. Okay, and so we're actually only taking $1,316 off the balance. Okay, so we minus the $1,316 from 8,000 to get our next balance, and then we repeat. So it's the same repayment. We work out our 0.5% of the current balance to work out the interest, subtract the interest from the payment to work out how much are we actually reducing the principal by, and then take that off. And we can continue that process. And again, we can see here that the last payment's been adjusted as we calculated in part C on the previous page, so that we get to exactly zero. If we left this at 1,356, we would have seen that this was out. This would have had $4.64 here, okay, as we saw previously. All right, let me just clear all those scribbles so we can see what's happening. We could set it up with an amortization table. As I said, you're not going to be asked to set up the amortization table in full. It will be more about working out missing values in the table. Let's have a look at an example using Finance Solver. So again, Finance Solver, we need to be careful about the sign conventions. So by that I mean whether we use negative or positive numbers. Okay, and that's going to vary depending on whether we have a loan or an investment. And so here we're looking at investments. So in this instance, the principal value is going to be a negative value, because remember, we think about the principal value and the payments as in terms of the direction of the money relative to me. So I gave the initial investment to the bank, the money went away from me, and so that's a negative amount. I'm then going to make withdrawals out of the investment. So I'm going to take money from the bank and bring it to me. So that's going to be a positive amount. Okay. Later on, when we'll look at investments where we might make deposits into the investment, it's possible to have investments where the payment amount is also negative because you're also paying those into the bank. But for these particular annuities, we're withdrawing the money, so it would be positive. And the future value in this instance is either going to be positive. So if we haven't yet withdrawn all the money, the future value will be positive. Remember, we think about the future value also relative to ourselves. So if that's a positive amount, that's because I have that money's owed to me. Okay, it's my money. If there's a negative amount, that's because that's money that I owe. So in this case, the investment, the money is mine. It's sitting in the bank. So a positive future value means that there is still money in that account that's mine, or we would take it down to zero. Obviously, the future value of an investment is not likely to become negative, because that would mean we've overdrawn the investment. We've taken out more money than we have, and we would have to pay that back to the bank. We might see that happen where we need to make final adjustments to the final payment or the final withdrawal, but generally speaking, we wouldn't let the loan go really into the negative zone. Sorry, the investment go into the negative zone. Okay, so again, using Finance Solver, all the same values, but this time it's really just about switching around where the positives and negatives sits. So if we have this example here, which is shown in the screenshot above, okay, it shows an $8,000 annuity, so the principal value is negative $8,000 because that was invested into the bank, paying interest of 6% per annum, okay, compounded monthly, so that's our 12, and there'll be a 12 in the CPY as well. And then the loan is to be paid out with 6 monthly payments, so the number of payments is 6, and the payments are $1,356. So the loan is being paid out to me as the individual, the money is coming from the bank to me, so that is going to be positive payments. And when we work out what happens, the future value of the annuity after those 6 payments has been made, the value is 4.64, and so we've still got, so this is the same example, Amy's holiday. We've then got $4.64 left after those 6 repayments, and so we make that adjustment to the final payment. Okay. All right, so that's all talked through in that box. Let's work on a new example. So Bianca invests $250,000 into an annuity, paying 4.8% interest per annum and compounding monthly. Okay, so I'm going to get my Finance Solver up here. So again, it will still have previous numbers in there from when I last used it. That's okay, we just override them. Okay, so if she wants to be paid monthly payments for 10 years, how much will she receive each month? Okay, so let's set things up. Let's work out what we've got. So N, so she wants to get monthly payments for 10 years. So it's going to be 10 times 12 compound periods, 120 compound periods. Interest rate is 4.8%. Remember, you don't adjust it. It's always the annual interest rate. Then what do we need? Principal value or present value. So the principal value or the value in at the beginning of this situation is $250,000. Now she invests that into the bank, so that's going away from her to the bank, so that's negative $250,000. Okay. Payment is what we want to work out. How big will her payment be if she wants this annuity to last for 10 years and take out monthly payments? Future value, we want to work out what payments can we take out to get it down to zero over that 10-year period. So we want the future value to be zero. And our payments per year and compounds per year, we're taking monthly payments, and so they will both be 12. Okay, so let's put that information in. 120 months, interest rate of 4.8%, investing 250,000, so negative 250,000. Withdrawing what we don't know, we want to work that out, so clear that box. Future value, we want that to be 0. Payments per year and compounds per year are both 12. Okay, so then if we scroll tab around to the payment cell again, press enter, the payment is 2627.27, and so therefore the monthly payment she can withdraw is going to be $2,627.27. Okay, so remember it's positive in the finance solver because that money is coming from the bank to Bianca. If she receives a monthly payment of $2,000, how long will the annuity last? Okay, so let's think about what we're expecting. If she takes out a smaller payment, we would expect the annuity to last longer. So we're going to expect N to be more than 120. Okay, so this time we want N is the unknown thing, and the payment changes to positive 2,000. Everything else is going to stay the same. Okay, so let's just adjust that. Payment's going to be positive 2,000. She's going to, sorry, 2,000, not 20,000. We still want to get it down to 0. We want to work out how long is it going to take to do that. So we delete the 120, we press enter on that, and we find that N is 173.63, so rounding to the nearest month is 174 months. Okay. Therefore, the annuity will last 174 months. So if we're interested in how much longer that is than 10 years, we can escape out of our finance solver, and we can do 174 divided by 12 to see how many years that is. Okay, and that's 14.5 years. Sorry, months. Which is the same as 14.5 years. Now the question asked to the nearest month, so we would leave it as 174 months, but just if we want to get a sense. So we get an extra 4.5 years out of our original investment if we decide that we can manage to live on just $2,000 per month. Okay, part C, what interest rate, correct to one decimal place, would allow Bianca to withdraw $3,000 each month for 10 years? Okay, so we know at an interest rate of 4.8, she can withdraw 2,600-ish per month for 10 years. So obviously we're going to need an interest rate higher than 4.8 so that she can withdraw $3,000 every month. Okay, so again, N is going to be 120. We're taking that back to 120. Our interest rate is now what we don't know. Our principal value is still the negative 250,000. Our payment, she wants to withdraw $300 each, sorry, $3,000 each month, so it should be positive 3,000. Our future value, we want it to be 0. We want to use up the annuity over a 10-year period, and our payments per year and compounds per year are still going to be 12. Compounds per year is still going to be 12. Okay, so let's go back to the finance solver, menu 8.1. 120 months. Interest rate is what we don't know. We want to withdraw $3,000. Everything else is correct. So let's tab back around to the interest rate and press enter here. Okay, so we would actually need an interest rate of 7 point, what does it say, one decimal place? So 7.7. So therefore, interest rate needed is 7.7%. Okay, so that's quite a big jump from the 4.8% we've currently got, so she's probably not going to be able to do that. Okay, so exercise 9E, some examples working with annuities. So that is compound interest investments, where you then withdraw the money to bring the value of the investment back down to zero.